In this video, we're going to look at how to calculate the average atomic mass of an element. We can also say that this is the weighted average of an element's isotopes. And isotopes are different versions of an element that have different numbers of neutrons in their nucleus. So, if we look at this first example in the yellow, if we have chlorine, if we have Cl35, there's 35 protons and neutrons in the nucleus, and Cl37, there's going to be 37 protons and neutrons in the nucleus. So if Cl35 makes up 75.8% and Cl37 makes up 24.2%, how can we calculate the average atomic mass? Well, we're going to use this following formula. We're going to convert our percentages to decimals, so essentially moving the decimal point 2 to the left for both, giving us 0.758, giving us 0.758 and 0.242. And we're going to multiply those percentages by their respective protons and neutrons that are in the nucleus. So for Cl35, we're going to do 35 multiplied by 0.758 because the 35 protons and neutrons makes up 75.8%. And we're going to add this to the remaining 24.2%, which is from the Cl37. So we're going to do the same thing except with 37. We're going to multiply it by 0.242, giving us a total of 35.48. So chlorine will end up with an atomic mass of 35.48, or roughly 35.5, because of its two isotopes, Cl35 and Cl37. If we look at how abundant they are, we can calculate our weighted average from that. Let's look at another example, this time with magnesium. So here we have magnesium 24, 25, and 26, all with varying abundance levels. So one thing you may have noticed in the last one is whichever isotope has the most abundance has the largest percentage, our overall atomic mass is going to be closer to that isotope. So since 78.7% is made up of Mg24, we can expect our overall weighted average to be relatively close to 24, more than 25 and 26. But let's find out for sure. So if we use our same formula, so our 24 times our decimal form of our percentage, so 0.787 here, we're going to get 18.89. Now for Mg25, we're going to do 25 times 0.101, giving us 2.525. And lastly, for Mg26, we're going to do 26 times 0.112, which comes out to be 2.912. Now when we add them all together, we're going to end up with 24.33 as the atomic mass for magnesium, which, like we said earlier, is closer to the 24 in the Mg24 than the 25 and 26, because the Mg24 is way more abundant than the other two. Well, what if we had to go in reverse? So let's say an unknown element has two isotopes, 10 and 11, as the atomic mass. Their average atomic mass is 10.8. What would the percentage of isotope 11 be? So we're going to have to work this reverse order. So we're going to start with our 10.8 total. And if you remember how we found it, it was our percentages multiplied by whatever values we had for our isotopes. So here we would have 10 and 11. So we did 11 times an unknown percentage. But how do we know the percentage for the 10? Well, if our total is going to be 100%, since it tells us there's only two isotopes total, 10 and 11, whatever percentage x is, The rest has to be 1 minus x if our total is out of 1. So we can write it as 10 times 1 minus x. Now we're going to end up with 10.8 equals 11x plus 10 minus 10x. When we add our like terms, we're going to end up with x equals 0.8. We did our 11x minus 10x, and then we moved our regular 10 to the other side. So x is 0.8. And if you remember in our formula, this is going to be the decimal form of our percentage. So isotope 11 makes up 80% of the total. Now, how can we have a rough check to see if we're correct? Well, if you remember, whatever the weighted average atomic mass is going to be closest to the one that's most abundant. Since we're at 10.8, we know that there's going to be more of isotope 11 than isotope 10. So that means that our percentage that we get as our answer should be more than 50%. We ended up getting 80%, so that's a good sign.